All right, you guys ready to do a problem involving plastic deformation and residual stresses for cases where we have axial loading in our parts? You guys ready for this? Okay. So here's the setup. I have this rod that is shown on the picture right here. It might be circular, it might be rectangular, it doesn't really matter, because the reason I would care what shape it was is that I would care to know what the cross-sectional area is of the different parts of the rod. Well, to help us out a little bit with this problem so that we don't get bogged down in too many details, I just gave it right at the beginning that for the left portion, it has a cross-sectional area of 3 square inches, and the right portion has a cross-sectional area of 2 square inches, okay? It says that this rod is composed of red brass, and we're going to assume that it has the properties that are listed for red brass in the properties table that we have in our textbook, which I have those listed here. The elastic modulus, it's going to be the same for both parts because this is all one material, 14.6 mega psi. And then the yielding strength is another thing that we're going to need to know. It is going to be 11.4, and this, sorry, I think this was supposed to be KSI, not MPSI. So it says here, which segment will yield first and at what load F? So this is our first thing we're supposed to answer. The next thing we're supposed to answer is what load will bring the other segment, whichever one of them doesn't fail first. How much load do we have to apply to where both pieces begin to yield? Okay. And then part C says, after unloading the rod from the load found in part B, what is the permanent displacement of point B? In other words, after I do these loads and take everything back off, point B won't necessarily be in the same location as it was when it started. And we're supposed to figure out how far will it have shifted because of the loads that were applied and then removed. Okay. And then part D says, what is the residual stress after unloading? And I specifically want to know what's the residual stress in both segments because it might not be the same. Okay? All right, so here's where we want to start with this process. This is a statically indeterminate problem, as you might be able to tell. Okay? This is pretty typical. You're generally going to see any time where you have residual stresses that pop up in these axially loaded cases, you almost have to have that in a statically indeterminate kind of a case. Otherwise, any kind of deformations that happen won't actually lead to additional loads. So this is not unusual for it to be this way. When we do statically indeterminate problems, we have a few types of equations that we can use, right? One of the types of equations is a compatibility equation. So I'm going to start with that one, okay? For this problem, when I'm talking about a compatibility equation, what specific physical point do you think I should be looking at to establish compatibility? Okay. To help out, I actually put down below here the load displacement relationships that I can expect just in general terms, right, below each one of these segments. So for the left segment, the change in length of the left segment, as long as everything stays elastic, right, the change in length of the left segment is going to be F sub AB, LAB over AAB times EAB, and similarly for this other one. This might give us an idea as to the variables we should be thinking about for compatibility. So tell me, what should our compatibility relationship be? However far point B moves, that's how much we will have changed the length of segment AB. It's also how much we will have changed the length of segment BC. And if we are willing to define a positive change for the left side as being compressive, like shorter, and a positive change for the right side as being tensile, we can just set the two literally equal to each other. That's our compatibility equation. Basically, it is delta AB is going to have to be equal to delta BC, right? With that kind of thing in the back of our head that says whatever direction of deflection for AB is actually going to be compressive, and the direction of deflection for BC is going to be tensile. Okay? Well, once I've established that, then I can actually take the details here and say, well, that says FAB times LAB over AAB times EAB has to be equal to FBC times LBC over ABC EBC. Do you agree with this? Okay. Now here's what I want to do next with this equation right here. What is FAB over AAB? That's force over area. Another way we could describe that is the stress in segment AB. So let me do a little substitution and say that is actually equal to stress AB times LAB over EAB. This is going to be equal to stress BC, for the same reason, times LBC over EBC. Fair, right? Because F over A is just stress in each one of those cases, okay? So now let me do another thing. Let me rearrange that equation to make a fraction between sigma AB and sigma BC. Okay, so I'm just going to rearrange this equation a little bit. On the right side, I'm going to end up with LBC times EAB, okay, over, then we're going to have LAB over EBC. Okay, everyone tracking with me so far? What can I say about my E values? Right, for this problem at least, I didn't have two different kinds of material. It's all made out of the same material. Okay, what if I did have one where I had different kind of material? Yeah, you would just have numbers there and you'd be able to come up with this fraction. For me though, that makes it just a little bit easier by those essentially being the same as each other. They'll divide out and just give me one, right? So the only thing that I'm left with is LBC and ABC, excuse me, LBC and LAB, right? What's LBC? 5 feet. What is LAB? 4 feet. So this just ends up being 5/4. How's this useful? Yeah, if I know one of them, I can find the other one, right? It makes a relationship between the stress value that I have for segment AB as for the segment BC, right? I can relate the two of them together, right? There is a big, asterisk, a big condition that is put on this whole little line of thinking that I just did for compatibility. What's the condition that I have to meet? So for all of this stuff right here, it only works as long as it stays elastic. Okay? Because the FL over EA equation assumes that you're in the elastic range of the material. So as long as my two pieces stay elastic, this condition is met. As soon as one or the other of them goes plastic, I can't use this anymore. With me so far? Okay. Is there any other way to get a relationship between sigma AB and sigma BC? Because this gives me one way to get that. What's another way? Tell you what, before I answer that question, let me answer this question right here. Okay. Based on this ratio, which of my two segments carries higher stress? This is before they reach plastic deformation. Yeah. So AB has higher stress, so it will fail first. And what stress level, when I say fail, I'm saying yielding, right? So what stress level will it fail at?
It's yield strength.
Yeah, this 11.4 KSI. So here it has a higher stress and it's going to fail at 11.4 KSI. Based on that, can I figure out things like how much stress and or how much force are in that part at the point where it begins to, actually fail? Because if you look at what we're asked to do in the first part, it says which segment will yield first and at what force F, right? So we just answered that it's going to be segment AB that fails first, that yields first. Can we figure out how much force? Sure, right? How do we do that? FAB at yielding, right, is going to be equal to whatever that stress was at yielding, 11.4 KSI, multiplied by what? Yeah, it's cross-sectional area, which was given up here at the beginning of 3 square inches, right? So when I put these in here, I end up finding that this is 34.2 kips. And that is the answer to the first question that I was asking up there. It says, which one is going to, well, it's not quite actually the answer. I should be careful. This is how much force segment AB is carrying. What is it actually asking me for up here? What load F, right? What load is applied to the body, right? Not what load this one segment is carrying. What load is applied to the body that causes our first yielding, right? So this number right here is not that value yet, okay? But I can get there from here, right? And one of the ways I can get there from here is I can notice that as long as we haven't gotten to where it has fully, like gone into the plastic range, in other words, we're right at the edge of the plastic range, it means both of these parts, you can still think of them as being elastic until you get up into the fully into the plastic range. So if they're both elastic, that means that my ratio still holds of sigma AB over sigma BC is equal to 5/4, right? Okay, so what that tells me is that, like let's say what I'm trying to find is my sigma BC, okay? What that's going to be is it's, think about this, it's going to be equal to the stress that I have in AB, 11.4 KSI. This times 4/5 gives me what this stress is in BC at the point where everything starts, or where AB starts to yield. And so that ends up giving me, let's see, 9.12 KSI. And if that's the stress in BC, what's the force in BC under these conditions? 9.12 KSI, what? Times the cross-sectional area of BC, right? And BC has a cross-sectional area of 2 square inches. And therefore I can multiply those together, and that ends up giving me 18.24 kips. Okay? So, how does that help me? Yes? Yes, so the question was, are both of these still in the elastic range? And the answer is, yes, both of them in the elastic range. AB is the one that's going to reach yielding first, right, between the two segments. And so definitely BC is still in the elastic range because AB reached yielding first. But even AB can still be treated like it's in the elastic range as long as we don't go above this value. If we're at the value, then we can still treat it like it's elastic, right? Not that you can go above the value, but if you continue to cause deformation while it's holding this stress value, right, that's when we have another situation where the piece is going plastic. In this case, it's not going plastic. Okay? All right. So how do I take these two and combine them together to figure out how much load was ultimately applied at point B? Okay? I suggest we'd look at some free body diagrams. Let's look at segment AB there, and let's look at segment BC here, okay? F, let's imagine F is being applied to segment AB right here, but segment BC is attached at this point, so it pulls back this way, and I'm going to call that FBC, okay? That means that's FBC pulling that way and FBC pulling that way, which means I have FBC pulling this way over here. What happens on this other end? Okay, yeah, or FAB, right? This is the FAB that I just calculated what that value was at the point of yielding just a second ago. It acts on this side of this part. So our equilibrium equation for part AB says what? FAB plus FBC minus F is equal to 0, which tells me that F is just going to be equal to FAB plus FBC. Okay? And with all of this in here like this, we can now figure out what force F will cause this rod to first yield in piece AB. Okay? All it's going to be is 34.2 kips plus 18.24 kips, and this is going to be equal to 52.44 kips. If I wanted to say this in a little bit more simple way, what I could say is I can apply up to 52.44 kips, the way that I have my rod shown in my picture, before I cause anything to begin to yield. All right, this is my limit That's my upper limit on how much force I can apply before I start to cause yielding. Okay? And that was what we were supposed to find in part A. All right? Any questions yet for that? So which segment will yield first and at what load? So we just said at a force of 52.44, segment AB, right? Maybe I'll put that to the side. Segment AB on the verge of yielding. Okay, so his question was, how do we figure out AB has a higher stress? That's what we did this thing right here for, right? As long as only one of them is on the verge of yielding, right? That means the other one is still elastic, right? And that means that if it's just on the if the one that is on the verge of yielding is only on the verge and not fully into where it has begun yielding, then all of these elastic relationships will hold. And because this ratio was 5/4, that tells me that sigma AB is larger than sigma BC. Fair? Okay, now the next part says, how much load would we have to apply to bring the other segment, segment BC, to where it's on the verge of yielding? Okay? Believe it or not, this is an easier question than the first one. Why is that? Okay. Well, no, see that once we go up past 52.44, so this number is going to be higher than 52.44, this relationship of sigma AB over sigma BC is no longer valid because we have it's especially not valid for part AB, right? Part BC, it still will demonstrate a elastic behavior, right, up till some other value, but AB will stop exhibiting elastic behavior above 52.44 kips applied. Okay? Believe it or not, it's even easier than what he suggested, right? Think about this. If both of them are on the verge of yielding, do we know how much stress is in both of them? Yeah, the yielding stress of the material is 11.4 KSI. And we are working using an elastic, perfectly plastic material model, which means it's going to be something like this, right? It means that after it yields, no matter how much additional deformation is put into the material, it's going to hold at the exact same stress level. Does that make sense? And that stress level that we're going to be looking at is sigma sub y. So that means both pieces of material have a stress of sigma sub y in them for this second part that I'm dealing with. Okay? So that means I can go down here and do 11.4 KSI multiplied by its cross-sectional area. You know, so let's say I'm doing AB first, right? So AB, the stress in that one multiplied by its cross-sectional area, plus the stress in BC, which is also the same, 11.4 KSI, because we're right on the verge of yielding, multiplied by 2 inches squared. This is it, right? Each of them is contributing the maximum amount of force that it can because each of them are right at the point where they are yielding. Okay? So if I put these together, this winds up being 57 kips. And this is an interesting result, partly because this rod literally can't carry any more than this. What will happen if I try to put more stress than this in the rod? Yeah, both pieces are going to wind up with their loads up in this flat part of this curve, which means there is no more force. So you have to go higher on the vertical axis to get more force. And these curves don't let you go higher on the vertical axis. And if both pieces of material have these load points up in the flat parts of the curve, there's no more force available. Both the pieces are going to be deforming plastically as opposed to, giving you more force. Does that make sense? Okay. All right, so that's part B. Let's do part C. Part C says, after unloading the rod from the load that you found in part B, in other words, let's say you put your 57 kips on there, and then you take the 57 kips back off, okay? It asks here, what is the permanent displacement of point B, right? Meaning there's no more loads applied, but point B is no longer in the same place as it was originally. So let me actually kind of sketch a picture of what we're trying to get to. So this was our rod originally, okay? Tell you what, instead of saying that, let me say our rod originally was maybe somewhere over here, Let's say that's my original spot where the rod was, okay? And then I applied my force of 57 kips, and that moved that point over here. So in other words, with my 57 kips applied, okay, and I'm going to put down below here, this is my loading, like in other words, not when I'm unloading, but when I'm loading. Does that make sense? So in the first part of the process, I loaded it up with this 57 kips, and that caused this point B to move to the position it's at now. And so tell you what, let me give that dimension there a name. Let me call that dimension right there, I'm going to call it delta loaded. How about that? Let me ask you this. Actually, before I even sketch anything more on my picture, is there a way that I have to figure out what this amount of movement of point B is going to be under this 57 kips of load?
Whatever the corresponding would be from just AB.
Okay. So I think you're on the right track, okay? So think about this. Because we're loading it right up to the threshold of where BC is about to become plastic, right? That's what this load is of 57 kips. That means it really hasn't gone plastic yet. It's right at the verge of going plastic, okay? That means for part BC on this curve that I was talking about right here, BC is literally sitting right on that little corner. That means that corner is actually part of both the slopey curve to the left, the slopey line to the left, and the flat line to the right. That's a powerful point right there, okay? The reason why is you actually still are obeying, if you're on that point, you're still obeying the elastic formulas that we know for this rod, okay? So what that means is that whatever force I have in rod BC, it's creating a certain amount of deformation there. And I can actually calculate that, right? So in other words, delta BC for loading, or loaded, is going to be equal to delta loaded. However much change in length happens for segment BC is going to be the same as however far point B moved. Is that fair? Okay. This is going to be equal to the amount of force in BC. Do I know that value? Actually, I know something even better. Think about this. Think about that this is essentially FL over EA for part BC when it's loaded. If you'll permit me to kind of use some, fairly inexact notation there just for the point of showing you that let me actually write this way, AE. Okay? For the point of showing you that inside of this formula is what? Stress. And what stress is that at this state of loading? 11.4 KSI, right? So this is going to be equal to 11.4 KSI. That's the F over A part of this thing. What's L? What was the L of BC? 5 feet. What was the E? Actually, we may not have used that just yet. E was 14.6 MPSI, or another way of saying that is 14.6 times 10 to the third KSI. Now, I don't really want this to end up in feet, which is what it's going to end up with right now. So let me put in here 12 inches per foot. And I will say here that this amount of deflection that has happened in rod BC, which is how much point B moved when it's under load, is going to be equal to 0.04685 inches. And so this is, the way I have it labeled up there was that this was delta loaded. Okay, now, we just had a little discussion here a second ago about when we unload these bars and we're dealing with plastic deformation, a better way of thinking about it, rather than just thinking about taking the load off, is to actually leave the load on and apply an equal amount of load in the same place in the opposite direction, okay? So let me do that here. Let me grab another color. Let's say I put another load here of 57 kips, and I'm put down here, this is for unloading, okay? Now what is this piece going to do in response to that unloading? It's probably going to come back this way a little ways, right? Maybe not the entire amount that it moved when it was loaded, because we've had this plastic deformation going on. Okay? So let me name that amount right there. I'm going to call this delta unloading. Now my question is this. When this is unloading, right, it already had the load pushing it to the left. Now we're having this load pushing it back to the right. Is anything deforming further, or is everything behaving more like it's elastic? It's elastic, because in order for that 57 kip force back to the right, in order for it to start doing more deformation that direction, it has to be more than 57 kips. It's going to have to push it all the way back the other direction to where you're causing there to be literally reversed stresses as opposed to just, you know, relaxing the stresses. Does that make sense? Okay, so that's what justifies this statement right here that says during unloading, both of our segments are going to behave elastically. Well, what does that mean? That means we're back to saying that sigma AB over sigma BC is equal to what? 5/4. Okay. Furthermore, what else do we know? Our equilibrium equation still applies as well, right? So for this little piece of this thing, we're going to say FAB plus FBC is going to be equal to F, which is 57 kips. Well, how can I transform these stresses to get them closer to FAB and FBC? What if I do FAB over what? Its area, right? Remember, it was 3 square inches of area over FBC over that one's 2 square inches of area, right? This is going to be equal to 5/4. Okay? And this tells me that, I mean, there's multiple ways that I can do this, but let me do it this way. I can say FAB over FBC is going to wind up being 5 times 3 over 4 times 2, which is going to be 15 over 8. Okay? And if I care to, I can rewrite that equation a little bit because what I want to eventually do is substitute back in to my equilibrium equation to be able to solve for something like, let's say, the force in BC under this unloading type scenario, right? So to get that, let's say that I want to eliminate AB and express it in terms of BC. Okay, so let me say that I rewrite this as FAB is equal to 15/8, right? Which means I can rewrite this equation like what? 15/8 FBC plus FBC is equal to 57 kips. All of that basically can be solved, and we find that FBC is going to be equal to what? I get 19.826 kips. And how's that helpful? Okay? Yeah, look back up here. I had my amount of deflection when it was loading, and then here, this is the amount of deflection that happens due to unloading, which is what happens in response to my 57 kip force that's pushing back. What's the final amount of permanent deformation? The difference between these two, right? This is our permanent deformation, okay? And so let me call that delta permanent. It's going to be equal to however much it moved to the left, which we just found was 0.04685 inches, minus however much this thing wants to move back to the right. Now I know how much force is specifically in rod BC, so I can use FL over EA for rod BC because rod BC has never started behaving plastically. It was on the verge of it, but it never got into where it was behaving plastically. So my FL over EA equation still works for it. That's an elastic equation, right? So I'm going to put in here 19.826 kips, that's F. L was 5 feet, over A was 2 square inches, and E is 14.6 times 10 to the third KSI, which this equation is almost everything I need. It's got one little units issue that I need to deal with. Feet. So I need to put this in 12, multiply by 12 inches per foot to get that in inches. And what you'll see there is that the kips is like, KSI is kips per square inch. So that force unit will cancel itself out. All the other units will come back to being inches. So anyway, after putting all this in here, I get that this calculates to 0.006111 inches. And that's the answer to that next piece, is like, how much permanent deformation do we have? There it is. This one right here, he wants to know, how did I find the 0.0? Yeah, it's in that work right there. This is FL over EA. So in other words, the amount, this is our delta loading, right? This is how much delta happened during loading. When we applied a force the opposite direction, a portion of that force specifically went into rod BC, right? That's what all this work up here was to figure out how much of the force that's applied during unloading actually goes into just rod BC. Because I know rod BC is behaving elastically, right? Since I know it's behaving elastically, if I figure out how much force it's carrying, then I can use that in FL over EA to figure out how much does that one rod change in length in response to the load that it's carrying. So I subtract that back off of the amount that it had moved under loading. That gives me how much it wound up moving at the end of the day. Okay, now the last part. What are the residual stresses after unloading? Okay, believe it or not, this one is not really that hard, because what we have to do is we have to say, how much force did we have in rod BC when it was loaded, minus how much force did rod BC carry when we unloaded it. The difference between those two is how much force is carried in the rod at the end of the whole process. Does that make sense? However much load it carried while it was loaded, minus however much force it carries in the process of unloading it. The difference between those is its final force that it's carrying. Well, I actually happen to know these numbers already, more or less, right? I actually have to do some calculation to get the first one, right? How much force did BC have when it was loaded? Well, I may not know the number, but it's going to be 14 KSI times what? 2 square inches. The reason for this is, again, remember, FBC, when it's loaded, it has its loading point on the stress-strain curve right there at that intersection between the two curves. Like I said, that's a powerful point right there, right? Because it means I'm also at a value of sigma y, right? So if I'm at that value of sigma y, all I got to do is multiply by the cross-sectional area. That gives me the force in rods BC when it's loaded, right? What about FBC when it's unloaded, or in the process of unloading? Well, I just calculated that one. It's 19.826 kips. And adding these together, I end up finding that FBC residual is going to be equal to 2.974 kips. Is that a residual stress? Not quite, but it's very related to them, because this is the amount of residual force is present. How do I get that into a stress? Okay, just divide whichever part that I'm looking at by its own area. This is the same force that's going to be present in BC as in AB, because there's no other forces present. However much force is in rod BC, it's coming from the fact that AB is putting a force on BC, right? So this same force is going to be present in both AB and BC. That means that if I want the stress in AB residual, it's going to be equal to this 2.974 kips divided by the cross-sectional area of rod AB, which was 3 square inches. And that gives me 0.991 KSI. What about sigma BC residual? Same number for the force, 2.974 kips, divided by, for this one, it only has 2 square inches of cross-sectional area. And so that gives me 1.487 KSI of residual stress in piece BC. Questions yet on the process there? Okay. I have something just a little bit extra for y'all. Okay? I want to show you a picture of what's actually going on. So this picture that I'm going to show you of what's actually going on, let me put the original bar on the screen here also. Okay? What's happening here is I've got this thing set up so that I can scroll through and show you all different values of force F during the loading process of this bar. Catching what I'm doing there? So I can grab the little scroll bar here, and we can move this across, and we can figure out what's going on for each of the two bars, right? Notice here, I'm increasing the amount of applied force. Everything's staying elastic, right? Notice here, the blue dot, that is for segment AB. The green dot is for segment BC. This over here on the left side is a stress-strain curve using the elastic perfectly plastic model. If I keep on increasing the amount of force, at some point, I hit somewhere around 52.5 kips, which that was right around what we calculated to be the transition point for AB, where it starts to be plastic. Notice where that point is on this curve, right? That happens when we apply a force of 52.5 kips to the rod. What if I keep on increasing the force? Okay. Notice that the blue dot is now into the plastic portion of that curve, but the green dot is still in the elastic portion of its curve. All the way up to the point where the green dot reaches that same point. Happens at 57 kips of applied load. Now, one of the reasons I wanted to show you this is so you can see over here the actual force displacement curves for each rod, right? So the blue curve right here is the force displacement curve for AB, and the green one down here is the force displacement curve for BC. Up here is the force displacement for the entire rod, right? So this is the entire amount of force being applied, and you'll notice there that the same type of things happens. Whenever we're doing force displacement, remember, displacement is the same for both segments of the rod, right? So these points always line up, which is why I showed that vertical line in this little thing. But you go along, AB hits its point where it becomes plastic first. What does that do to the force displacement curve for the whole thing? Changes the slope. Why does the slope change right here? Yeah, the blue line just becomes a constant as opposed to constantly increasing as you increase the amount of load. Does that make sense? So that changes what that slope is. You keep loading it, and finally you get up to the point where the other one reaches its max, and you have that, then the whole thing becomes flat. What if you try to increase load after that? It can't take more load. It'll just deform without bound. Okay? Cool, right? All right. Hopefully that was interesting at the very end there. Questions? Any other questions? All right. Have fun.